Okay, so today we're going to learn about slopes of parametrized curves. And in order to understand that, you need to have a basic understanding of parametric equations. So parametric equations can be used to describe the motion of a particle in the coordinate plane. So we're still working with our xy plane. This is our rectangular coordinate plane. Our Cartesian coordinate plane, however you would like to call it. And we still have each point that is plotted as x comma y. I'm going to label that as x sub 1, y sub 1. Okay, and so each point that you're plotting is actually connecting a path that a particle is taking in the coordinate plane. And this particle is moving with respect to time, so we have a parameter here, t. T is representing time. And so when the particle is moving in the xy plane, we have not a regular ordered rectangular equation. We do have an ordered pair, but we don't use a rectangular equation to represent that motion of the particle or body moving in the plane. We have parametric equations. Okay, we have two equations. That's why it's plural. One is a function of time. The other one is more than likely a different function of time. But that gives us the location of the particle and the path that it represents. So if, let's say, you have a function of time and t is 0, and you get the x value to be 0, and you use t equals 0 in the next equation, you also somehow get 0. Maybe that is your initial point, and the next place the particle goes is here. So maybe it connects in this way, and the arrows don't represent continuity anymore, but they represent the path that the particle is taking. Okay, so you can kind of continue to put arrows along the way, or perhaps this is confusing you because it's not continuity. You don't have to put in the arrows, but it is important to know the path that the particle is taking. Okay, so with that being said, you can see here that you should be copying this down anyway, along with what you have in your do now. T is the independent variable. That makes sense because, as I was talking about, if t is 0, that's the initial location the particle or body is located before it starts moving along its path. So you would plug that in to each equation, and that makes not only y our dependent variable, we're very used to that being our dependent variable, but also x. Okay, and luckily that does give us different points to plot to get what's called the plane curve. The plane curve is the path that the particle is taking. And as such, and as described already, x equals f of t and y equals g of t are what we call our parametric equations. All right, so that was a lot to kind of go over. I feel like I even did it in one breath, so I'm sorry if I kind of rushed through it. You can watch the video again and get a refresher on that if necessary. So it's important that we do have parametric equations. And with that being said, we can apply it to calculus. Or perhaps the proper way to say that is that we can apply calculus to parametric equations. So here we go. The reason we would want to do that is to find the derivative, okay, the slope of our tangent line to our path that we have here. And dy over dx is found by doing this fraction here, okay? Basically, this makes sense, very similar to what we were describing with chain rule. Okay, dy over dt is divided, so if you do keep change, flip, by dt over dx. Okay, and so that makes sense. Okay, that's dy over dx. But when you are taking the derivative of the y equation, and it's in terms of t, it makes sense we write dy over dt. And if we have a separate x equation in terms of t, we'd have to say we're doing dx over dt. So therefore, okay, we have this fraction ready to go to find dy over dx. Okay. The only thing is, and as you should be writing this down, this is also your notes, dx over dt cannot be 0. And as you can see, it's because it's our denominator. We can't do anything if our denominator is 0. So we don't like when that happens. Okay? And we're off to do our example. So as soon as you get that down, we should be starting. Okay, I'm going to read it first. It says, find the line tangent to the right-hand hyperbola branch. Define parametrically by x equals secant t, y equals tangent of t, and we're going from negative pi over 2 is less than t is less than pi over 2 at the point radical to 1, where t is pi over 4. Okay, here's what you need to understand. Okay, we're looking for the line tangent, so we need a dy over dx. Okay, that's the slope of our tangent line. It doesn't matter to what curve, okay, whether it's a hyperbola or not. And because our parametric equations are defined as trigonometric functions, okay, our angle measures can be described as negative. Okay, our negative angle measures go clockwise away from 2 pi. So there is a way in which we can represent that as a positive t value, but we're not going to here. Another thing with t is that we like to look at t as just positive because t is time. But again, when it comes to trigonometry, our negative angles are also positive angles. So it's okay if we plug in negative values if and only if they are angles. All right? So don't worry about any of that. Now, when you have to find the line, you need a point, okay? And we also need a t value we're working with because it's with parametric equations, so that's where they give us the t value, okay? So don't worry about everything else that's described. It will work out naturally. Here we go. Let's start it off. So in our example, the first thing that we want to do is look at our x equation and find dx over dt. So dx over dt is secant of t tangent of t. Great. Then we want to take our y equation and find dy over dt. Okay, that is secant squared of t. That's fine. So now, dy over dx is when we take our dy over dt and divide it by our dx over dt. And we can cancel factors. And that means that dy over dx is secant of t over tangent of t. This is fine even though it looks like we have different variables. That is because we're working with parametric equations. Okay? So that is where our t value comes in. We want to plug pi over 4 into our expression. Okay? And at that point, we find dy over dx. So secant of pi over 4, okay, is the same as 1 over cosine of pi over 4. And the cosine of pi over 4 is 1 over radical 2. And tangent of pi over 4 is 1. And so I apologize. So like I said, secant is 1 over radical 2. So let me fix this. Okay, so this ends up being radical 2 over 1 right here. Okay, I apologize. And if I'm dividing by 1, it's still radical 2 over 1. So this final answer, I'm going to squeeze it in, is just radical 2. Okay? So now, we're almost done. We found dy over dx. So that means we found the slope to our tangent line. So let's start working on our tangent line. So our tangent line is y minus y sub 1, which is 1. Our slope is radical 2. And we have x minus x sub 1, which is radical 2. A lot of radical 2's here. I think that's what happened. And we end up simplifying this to be y equals radical 2x minus 1. And that is our line, tangent to our curve here, set by our parametric equations between our t values at a certain point when t is this value. We're all done, okay? And the key thing is to understand to take your time. Find dx over dt, find dy over dt, find dy over dx, okay? Substitute. Okay, be careful when you're substituting. If you say 1 over cosine, make sure you write 1 over cosine. And then just use the slope and your point slope form to get your line. All right, good luck.